So I'm glad to see everybody that's here. You've gotten your test 1 results back. And so let's just move forward. And hopefully, if you didn't do as well on test 1 as you would like to do, that can inform you about the kind of maybe time that you need to spend on material in order to do better down the road here. For a lot of students, it's sort of a shock, right? How much work this course takes. So I'm hoping everybody is just going to plug away and keep playing. And let's move on. Okay. So tonight, the announcement is there will be an office hour right after this class, so that if you need some help on that Chapter 4 special homework, your first homework on writing proofs, we can talk about those problems. So that's our announcement for tonight. Tonight, we're going to have one more proof involving the definitions of even and odd, just to make sure everybody feels comfortable. We haven't actually done a proof with the definition of odd, so let's do that. Then we're going to talk about the rational numbers, which is section 4.3, and we'll look at several proofs and a disproof in that section. And then we will start the section 4.4, which we will finish on Wednesday. So your next web assigns are up. The web assign that was that's due tonight, no, it was due last night, was on the calendar and in WebAssign, but it didn't get onto the reading page, and that's my bad. So if you need an extension to the WebAssign 4.1 and 4.2, just put that message through the WebAssign app, and I will give anybody an extension who asks for that. But the WebAssign is already posted now for this material that we're going to cover tonight. All right, so here's our do now problem, just to kind of get warmed up. Let's just practice good steps 1 and 2 so that we can write a proof of this statement. The sum of 3 odd numbers is odd. So see if you can write that as an if-then statement. That'll be what we start with this evening. You can don't want to dive into the definition of odd at this point. We just want to look at the idea that the sum of 3 odd numbers is odd. So we want to give those numbers names. And once they have names, then we can start talking about them and applying the definition of odd to those numbers. And we're going to learn some interesting things tonight about definitions. So let's go ahead and start with that. This is our example 1 tonight. So here we go. Let's call them, say, X, Y, and Z. You could use A, B, and C. You can use any letters you like, but the point is we need 3 of them because we're talking about 3 odd numbers. So if X, Y, and Z are odd, and you can say odd numbers if you like. You don't have to. You can just say are odd. We know we're talking about numbers. Then, okay, so how do we talk about the sum of 3 odd numbers if we are naming these odd numbers X, Y, and Z? What would be our expression for the sum?
Then X plus Y plus Z is odd.
Exactly. So that's our first step, folks, is to write the statement as an if-then, because we know the minute we've written it as an if-then statement that we got our eyes on the hypothesis of the statement, and that's what we're going to assume, that X, Y, and Z are odd. And then we can see very clearly what the conclusion is, and that's what we wish to prove, that X plus Y plus Z is odd. So that's both good step 1 and 2. We always want to write our universal statement as an if-then. And clearly this is about all odd numbers. Even though we don't explicitly see the word all, this is a universal statement, okay? So let's look at a proof. We're going to indicate where the proof starts, of course. and we're going to assume the hypothesis. So our first step here is just to go ahead and assume X, Y, and Z are odd. You can say integers if you like. You can say numbers, you can say integers. I'm going to write it both ways. X, Y, and Z. Assume X, Y, and Z are odd. I'll put integers here. But you could say numbers, or you could just say are odd. We know we're talking about integers if we're talking about odd numbers, right? Now let's look at our thinking notes. Remember, we want to denote that with square brackets. What do we wish to show? Well, we wish to show the conclusion that X plus Y plus Z is odd. Why do we want to do this? Well, this is direct proof method of an if P, then Q statement. We assume P, and what we wish to show is that Q follows. That's always the game with a direct proof, okay? So now we just dig in and we realize that the definition in play is the definition of odd. So we're going to have a bunch of equations. Here we go. By the definition of odd. And this should be good review. What do we see? Well, we see that X is equal to, say, 2K plus 1, where K is an integer. Remember, the definition of odd has two parts, okay? We're getting two good pieces of information because X is odd. We get this nice equation, and we get information about the integer K, excuse me. Y is also odd. So Y is equal to, but we can't use K because we don't know that X and Y are the same. They might be the same, but we can't assume that. So let's pull out another letter, say J. So Y is equal to 2J plus 1, where J is an integer. And finally, we're going to have one more odd number, that's Z. And I'm going to say is equal to 2 times N plus 1, where N is NZ. Listen, your choice of variables here is pretty much irrelevant. Just give X, Y, and Z their own integer, whatever you decide to call it. Now, I'd like to expound on this wish a little bit because if we know exactly what it is we're trying to do, we have a lot better shot at achieving that. We want to show that this sum, X plus Y plus Z, is odd. So let's go ahead and expound on that wish. What we wish to show is that X plus Y plus Z is equal to, say, 2M plus 1. Where M is an integer. So that's an expounding on our wish. And this is a good habit to get into, folks. You see, when we expound on our wish, then it gives us a really good look at the expression that we actually have to examine. In this case, what we need to examine is the expression X plus Y plus Z. And we're going to try to show it looks like 2 times an integer plus 1. And of course, the M that we get is going to be written in terms of the K and the J and the N that appear in these definitions of these variables X, Y, and Z. All right, let's continue. Observe. Why do I say that? Well, because I can't start a sentence with a lowercase letter and X is a lowercase letter, so I just stick a word in front of it. Here we go. X plus Y plus Z is equal to, and now we use substitution. We're using part 1 of the definition of odd to prove part 1 of the definition of odd. What do I mean? We're getting ready to try to get X plus Y plus Z to look like 2M plus 1. That is part 1 of the definition of odd. So the game is to prove part 1, we're going to be using these part 1s. We're just going to substitute in. X is 2K plus 1. Y is 2J plus 1. So we put a plus between those, plus Z, and Z is 2N plus 1. So there we have those. Okay. Now, we want to get it looking like 2 times something plus 1. let's just rearrange these expressions for x, y, and z so that we can get some 2's pulled out. We've got 2k plus 2j plus 2n. We see, those 2's, but here we've got plus 1, plus 1, plus 1. So that's a grand total of plus 3. Now, the definition of odd does not say that x plus y plus z looks like 2 times an integer plus 3, okay? It needs to be plus 1. So whatever we have here, we're going to need to rewrite it so that we can see the plus 1 hanging off the end. So we can rewrite the plus 3 this way. We can write this as 2k plus 2j plus 2n plus 2 plus 1. You see, and now we've got that plus 1 where we need it here at the end, and we can go ahead now and pull a 2 out of these first 4 terms, and we have k plus j plus n plus 1 quantity, whole thing plus 1. And that is part 1 of the definition of odd. You see this expression right here, this is going to be our m. And we have to talk about that because what we have to prove now is that m is an integer. So we're going to use the closure properties. K is an integer. See, that's this piece of information here. We haven't used that yet. J is an integer. You see, we're going to use that now. N is an integer. So we're using part 2 of the definition of odd to prove that this m is an integer. We're using part 2 to prove part 2. So let's write that up. So we can let m equal the quantity k plus j plus n plus 1. And now we talk about everything we know. Since k and j and n are in z, and you can just write it like that. Since they're all in the same set, we can just separate them with commas and say it all in one fell swoop. And z is closed under addition because that's the operation that's being used here to build m. Addition is being used, and that's the only operation. So it's the only one we need to mention. Z is closed under addition. That's one way to say it. We know m is an element of z. We know m is an integer. So now we can just wrap it up. So x plus y plus z is equal to 2m plus 1, where m is in z. Which means x plus y plus z is odd by the definition of odd. When we use the definition of anything, we say that we're using that definition just to keep our reader, straight. So we've used our equations for x, y, and z to build an equation for the expression x plus y plus z. And then we talked about this factor being an integer. And that way we have addressed both parts of the definition of an odd number and successfully proven that that expression is odd. Any questions? We're going to see this idea again and again tonight, where if we have a definition that has several parts and we want to prove something satisfies that definition, we'll use corresponding parts to prove corresponding parts. All right, so this is the last that I'm going to do from sections 4.1 and 4.2. Your special homework is all about evens and odds. I think there are 3 proofs and 2 disproofs. I think the 5th problem in the special homework, I actually asked you to figure out if it's true or false. But if you look at the day 10 notes, the answer to that question is in those notes. It was a do later right at the end of those notes. So you've been given a big fat hint there. All right, so we're going to go ahead now and move into section 4.3, the rational numbers. Every real number is classifiable. We can classify it as either rational or irrational. And that's kind of a nice thing. And depending upon, where you went to high school, you may have learned a different definition of rational and irrational than we're going to use tonight. One of the definitions of rational and irrational goes like this. A real number is rational if its decimal expansion eventually repeats. You might have heard it phrased terminates or repeats, but terminates means it's zeros forever after, and that's the same thing as getting repeating zeros. Like 1/3 is 0.333 forever, right? We usually put a bar over the 333 part. So, I mean, you've probably heard of that definition. Sorry about that. My little setup here is slipping. Okay, there we go. And then an irrational number has a decimal expansion that never repeats, like the expansion for pi, right? Have you ever had that friend that can, state, pi to, 50 decimal places or 20 decimal places or something crazy like that? That's one way to define rationals and irrationals. But the way that we're going to define rationals is actually quite a bit more practical for our applications, and it's equivalent logically to the definition that I just stated about terminating and or repeating decimal expansions. So here we go. Let's define the rational numbers. By the way, the set of rationals is denoted by a double bar Q. The same way that we use like a double bar R for the reals or a double bar Z for the integers, we use double bar Q, and it stands for quotient. What is going on? I guess we're just going to have to deal with it. My goodness. I apologize. I say, good Lord. What is going on? Oh, I see what it is. Hang on just a sec. The little sucker thing that holds us down has finally lost its grip. So I gotta get it to grip again. There we go. Stay. Okay. Here we go. The set of rational numbers. That's what we're defining. First, we'll look at the whole set, and then we'll look at individual rational numbers. The set of rational numbers, there should be a space between those, denoted by Q for quotient, is defined as follows. Double bar Q is the set of numbers A over B. So they're expressible as quotients. Now this vertical line, in case you don't remember from way back when we talked about sets, we read as such that. Such that A is an integer, so A is in Z, B is in Z, and we know we can't divide by 0, so the other caveat here is that B is not equal to 0. Now, in other words, let's write this a little bit differently so that we can apply it to a single rational number. A real number X is rational if X is equal to A over B, and we can put A and B together in Z, where A and B are in Z, and B is not equal to 0. So that's the definition of a rational number. Let's count the parts of this definition, folks. First, we have this nice equation for X. So that's part 1 of the definition of rational. Then we have this information about A and B, the numerator and denominator. They have to be integers. That's part 2 of the definition. Finally, we know that B is not equal to 0, so we could call that part 3 of the definition. So the definition of rational has these 3 parts. So we get that when we know something is rational, and we have to prove that if we want to prove something is rational. All right, so now let's look at our example 3. Oh, example 2, my bad. Here's a claim. Every integer is rational. That's the claim, that every single integer is actually rational. Let's do good step 1 and good step 2 right now. Can you write that as an if-then? It's definitely universally quantified. So let's write that as an if-then. How about this? If n is in Z, in other words, if n is an integer, then n is in Q. N is rational. So we've given a name to the integer. And now we know that if we're going to prove this claim, that we have a hypothesis, which is super simple. We're just going to assume that n is an integer. And what we wish to show is that that will allow us to show the conclusion that n is actually rational. Super simple statement. Every integer is actually a rational number. How are we going to prove that? Let's look at the definition of rational. If we've got an integer n, we need to be able to write it as a over b, where a and b are integers. Anybody got any ideas about how we could make that happen? Let's look at the gallery. Let's see if anybody's got any ideas about how we could make an integer n look like an a over b.
Can't you do like n over 1?
Exactly. It's that simple. Like we always can write x as x over 1. We can write any number like 5 as 5 over 1. We can sure do it with n. So that's what we're going to do. Let's write n as a rational number by using the fact that we can just say, hey, that's equal to n over 1. Here's the proof of our claim. And there's our definition of rational where we can see it. Super simple hypothesis. Let's just give ourselves an integer. Assume n is an integer. You can say the words is an integer if you are more comfortable with that. Or if you prefer fewer keystrokes like so many comp sci people do, you can say element of Z. They mean the same thing, of course. What do we wish to show? Oh, we wish to show that n is rational, that it's in the set of rational numbers. And now we just do this super simple algebra. And since I don't want to start a sentence with little n, right, I'm just going to stick a word in front of it like observe or notice, or you could say, you know, we see, just something to start a sentence with a capital letter. N is equal to n over 1. Okay, now that's part 1 of the definition. We've got n looking like something over something, n over 1. Well, now let's talk about those parts, the numerator and denominator, being integers. We can just say it. We know n is in Z. If you want to say by hypothesis, you can, but you don't have to. And 1 is in Z. We know 1 is an integer, right? Nobody, there's no big mystery there. So we've just addressed part 2 of the definition of rational by simply stating them. Later, we'll have more interesting things that we have to do a little algebra. But in this particular example, it's super simple. Finally, we need to verify that the denominator, which is 1, isn't 0. You can just say that, right? Also, 1 is not equal to 0. So n is rational by the definition of rational. Or you could say i.e. n is an element of Q. Super simple, not a lot going on there. By the way, if you want like to kind of see visually how the numbers are related to each other, we could draw a little picture. Like it's called a Venn diagram. Like here are all the real numbers. Let's stick them all together. There's the reals. Well, the rationals are certainly real. So here are the rationals. They're a subset of the reals. But now we've just proven that the integers are all rational. So the set of integers is contained in the set of rationals. In other words, we have this nice nested subset inclusion. Z is a subset of Q, which is a subset of the reals, which of course Z is a subset of the reals. There's a transitivity of the subset inclusion. And we'll talk about that property, transitivity, later as we get deeper into the game of proofs. But here's just a little picture that kind of shows you the relationship between these sets of important integers, reals, and rationals now that we're looking at. All right, let's do a more interesting example. I am going to keep the definition of a rational number where we can see it. Because it's just handy. This is the really good time of the year to start that glossary, start a little notebook or maybe the back of your notebook, like save the last 4 or 5 pages and start writing definitions because it's really nice to have a handy, ready reference for definitions. Here's example 3. Prove the product of any two rational numbers is rational. Prove the product of any two rational numbers is rational. This is sort of a classic. There are two kind of classic proofs that we're going to do tonight. One is about the product of two rationals, and the other would be about the sum of two rationals. We'll do both of those tonight. All right. So it's the usual game. The usual game. We're going to write it as an if-then statement so we can get our eyes on what we're going to take for our hypothesis and also get our eyes on the conclusion that we wish to show. So you're going to see this over and over. Do good step 1 and good step 2 so that we can really see what we're trying to do here. Here we go. We're not going to include the word prove. We're just going to try to write the product of any two rational numbers is rational. And you can pick any letters you want, but listen, at this stage of the game, we're not going to dive into the A over B, okay? We just want to name these two rational numbers. Then we'll dive into the definition of rational when we're deeper into the proof. Right now, we just want a simple hypothesis. So how about this? If X and Y, we can call them X and Y. You could call them, something else, but I'm going to use X and Y, are rational. And you can say are rational numbers if that makes you feel more comfortable. Then, well, what's our then part? What should we write for our then part? We'd like an expression.
X times Y is rational.
Yes, beautiful. Then X times Y is rational. Okay, guess what I'm going to do right now? I want to reward everybody that's here. I'm going to do a quick attendance check. While I'm doing an attendance check, please go ahead and identify the hypothesis and the conclusion and start your proof by writing what you want to assume and writing what you wish to show, okay? So go ahead and you work on that. And this is what I'm going to do, folks. I'm going to make this really worth your while. Everybody that's here, I'm going to add 2 points to your test 1 grade. I know, that's non-trivial. Now, hey, there was 100 in this class. Congratulations. There were some very nice scores in this class. So, I mean, I'm talking 108 over 100, kind of 100, somebody got the 8-point extra credit. So, But nobody's going to mind 2 extra credit points on a test grade. So I want to reward you because I know it's discouraging, you know, sometimes when you're deep in this. Okay, so Zane, Gabriel, Kendall, Eric, Marcus is here, Brianna is here, and you'll see this change tonight in the grade book. Edwin, Danny, Nick, Matthew, Ronnie. Good to see you, Ronnie. It's nice to see the person who's saying if you want your 2 points, you got to pop onto camera unless you're driving. Hossein? Last chance to either chat in or mic in or pop on your camera, Hossein, if you're here. Oops. Maybe I'll check in a little while later. Maybe he just stepped out to the bathroom. Okay. Yep. I'm adding 2 points to your test 1. Okay. All right, let's get back to our work at hand. All right. So what are we assuming? Well, we're assuming the hippopotamus, right? The hypothesis that X and Y are rational. And we wish to show that this product is rational. Here we go. So assume X and Y are rational. And I'm going to just add the word numbers, but you don't have to. You could just say rational. And we wish to show X, Y. And I'm going to say is an element of Q. It's not thinking notes. I can write them any way I want. In fact, this is perfectly legitimate notation, even in a formal proof. That's fine. We want to show that the product is rational. Here we go. Break out the definition by the definition of rational. You hear the voice, right? The Halloween voice. Use the definition. We have, all right, here we go. X is equal to, I'm going to say A over B. Whatever letters you use are fine. Where A and B are in Z, and B is not 0, of course. And, of course, Y is rational. I like to go ahead and say C over D, where C and D are in Z, and D is not equal to 0. By the way, if we needed yet even another one, if we needed a third one, you could use like E over F, you know, A, B, C, D, E, F, right? Okay, now let's expound on our wish. Let's expound on that. We wish to show X, Y is equal to 3 parts. I'll say M over N, where M and N are in Z, and N is not equal to 0. Okay. And now we got to do a little bit of algebra with fractions, so we get a nice little review. When we're multiplying 2 fractions together, A over B times C over D, just in case you're a little rusty. You can remember it this way. You do it bikini style. You multiply the tops together and you multiply the bottoms together, right? So it's AC on top and BD on the bottom. This is part 1 of the definition of rational. We've got XY looking like something over something, right? And we used part 1 of the definition of rational to get this, right? We used this nice part 1 of the definition that X is equal to A over B, and part 1 of the definition where Y is equal to C over D. We just used those 2 things here. And now we've got part 1 of the definition of rational satisfied. Now we got to do the rest of it. We've got to show that AC, that's going to be our M, is an integer, and we have to verify that B times D, which is our N, is also an integer. Well, to do that, we're going to use the fact that A and B are integers and C and D are integers. See, that's what I mean in this game. To get part 2 of the definition of rational, we use part 2 of the definition of rational. So let's write that up. since we can say it all in one fell swoop, A, B, C, and D are integers, or you could say element of Z, it's okay. What do we know? Well, we're going to use closure properties of Z here. Are the operations that we're using to build M equals AC and N equals BD? What are the mathematical operations that are in play there? Anybody?
Multiplication.
Yeah, we're just multiplying A times C. So we're using multiplication to build AC. Same with B times D. We're just using multiplication. So we know M equals AC and N, I'll just name them, equals BD, are integers. Don't forget to say why, because I'll just write it a different way. Instead of saying because Z is closed under multiplication, I'll use the other wording, which is because products of integers are integers. You can use either wording that you want. But we're basically dealing with the closure of the integers under multiplication. So, hey, we just got part 2 of the definition of rational satisfied. We just showed that AC, which we're calling M, is an integer, and we just showed that BD, which is our N, is an integer. So we're almost home. All we got to do now is use part 3, which is that B and D are not 0, to get part 3, which is that product, BD, which we're calling N, is not 0. Here we're going to break out the contrapositive of the 0 product property, okay? That was something that I've been asking you to look at for a while. And now we actually have to really use it. Here we go. Finally, we'll be using these two things. Just say, since B is not equal to 0 and D is not equal to 0, the 0 product property, I'm going to write it here, but mostly we'll say ZPP. I'm just going to write it for the notes because I think we've only used it once before. The ZPP by the 0 product property says N equals B times D is not equal to 0. All right. So we just got that denominator, BD, which we're calling N, is not 0. So now we just kind of wrap it up. It's kind of like giving, a talk. You tell them what you're going to say, you say it, and then you tell them what you said. So let's just wrap it up. So X times Y is equal to M over N, where M and N are in Z and N is not equal to 0. It's a helpful thing for you too, because what that does is it kind of forces you just to double check, did I really address all the parts of the definition of rational? Which makes XY rational by the definition of rational. And we did it. All right, so listen, folks, a couple of words to the wise. Make sure you have some really good gel pens. If you use pen, something that writes really easily. If you're using mechanical pencil, I recommend a 0.7 HB lead, something that's not too hard, not H. H is too hard, but HB is nice. 0.7 HB is darn near perfect for writing smoothly and easily. It'll just like ease the pain, because sometimes it can get really tedious. So make sure you've got good writing utensils. It makes a difference in this particular job. All right, so we've just proven that every integer is rational, and we've proven the product of any two rational numbers is rational. Let's now practice a disproof, okay? Let's do a disproof. Consider this false claim. I'm going to write it as an if-then just to make our life a little easier. If X and Y are rational, then X over Y is rational. So that's actually a false claim. So, what we're going to do, folks, is we're going to do some scrap work to try to find a counterexample. This is a universal statement, okay? We know every if-then is a universally quantified statement. So when we disprove a universal statement, we're proving its existential negation. Sound familiar? And that's called giving a counterexample. So let's do a little scrap work to find a counterexample. To disprove the claim. So that's what our goal is. By the way, it might actually be helpful to write the negation of the claim so that we know exactly what we're proving. So here's a helpful hint. Write the negation. Which is what we're going to be proving. So, hey, folks, this is an if P, then Q. Right? It's an if-then statement. If P, then Q. So, here's where, it matters. We got to be able to negate if P, then Q. And that would be a P and not Q, right? That's the negation. P happened and Q failed to follow. And let's go ahead and put the existential quantifier in it. We know this is a for all, even though it's not written. We know it's a for all. That's what if-thens are. So we might go ahead and put the quantifier here and write the negation. There exist numbers X and Y such that P, in other words, X and Y are rational, and not Q. X over Y is not rational. So again, learning how to negate an if-then wasn't purely academic. You really need this stuff. Let's do a little scrap. Any ideas how we could find a rational number X and a rational number Y, where X over Y is not going to be rational? Like, think about it. We're gonna, how could this happen? Let's look at what it would look like to have, X over Y if X and Y are rational. It'd be A over B, that would be X, over C over D. This is a good time to review dividing a fraction by a fraction. Everybody remembers that that's A over B times D over C, right? You flip the denominator and multiply. So in other words, we're looking at AD over BC. How could it be that this could fail to be rational?
If X and Y are the same rational number,
You know what? If X and Y are the same, it's not going to be a problem because it'd be A over B divided by A over B, and that'll just always be 1, unless they are the same rational number where it's a bad rational number to try to use. There is one kind of way this can go bad. Let's look at the definition of rational. It's something over something where the denominator and the numerator, these two somethings, are both integers, but the denominator cannot be 0. So B cannot be 0, And D can't be 0 because these are going to be rational. But look what happens. Look what happens when we actually do the division. That D is no longer in the bottom. It comes up to the top. And the C is in the bottom. What if C was 0? It'd be okay for C to be 0 when it's on the top because that's just 0 over like 1, and that is rational. Zero is a rational number. We could write it as 0 over 1, right? Every integer is rational. 0 is an integer, it's rational. But what happens, you see, when we do this divides operation, that C comes downstairs and makes this denominator go bad. That won't even be defined, much less rational. So this is sort of a classic counterexample. Things can go bad if you're playing games with two rationals, and this is one of the ways things can go bad. Let's see if we can write this up. This is called a counterexample, okay? Because we are countering the original claim, which was that X over Y is rational. We're countering that false claim, okay? So, hey, you can just pick your favorite rational number for X. We're finding an example of numbers X and Y where X and Y are both rational. We're gonna pick 0 if that's rational. But I'm gonna, pick your favorite, number that's rational for X. I'm gonna pick 3. But you can pick any rational number. You could pick like 1/2 if that's your favorite rational number. It'll still work out. Consider X equals 3 and Y equals 0. Now, let's just take a moment and remember the two things we have to do when we are proving an existential statement. The first thing we have to do is verify that our choice of objects live in the correct domain. That's part 1. If you look at the notes from last time, when we're proving an existential statement, you have to prove that the objects that you say exist in the correct domain. So we're going to verify that these are both actually rational. Then we verify the property, and that is that X over Y is not rational. Okay? So here we go. Since we could just say it, 3 is equal to 3 over 1, and 0 is equal to 0 over 1. Clearly, 3 and 0 are rational. So they live in the right domain. They're both rational. Now 2. I want to say but. Once in a while, it's okay to start a sentence with the word but. But X over Y is equal to 3 over 0, which is not a number. It's not even defined. So it's not even a number. It is undefined. So X over Y is not in Q. In other words, it is not rational. You can write the words not rational, or you can use our symbolic notation, not an element of Q. Your choice, doer's choice there. I'm just trying to write things, a couple of different ways so that you can see that there are choices there. Okay, so now we're going to do one more proof with rationals. We're going to start it off together, and I'm going to leave you to do later the rest of the proof, the entire proof is in the class notes that are actually already posted, but try to write the proof without peeking. And that way, when you check the notes, you can, you can check, hey, did I do everything, that was done? It's just kind of a freebie chance to actually get some practice. Here we go. Example 5. Prove the sum of two rational numbers is rational. All right, so let's start this together. We'll do good step 1 and good step 2. Let's write it as an if-then, introducing variables so that we can talk about these two rational numbers. Let's just use x and y. I'm going to write using a slightly different notation, again, just to emphasize that you have some choices there. If x is an element of Q, that's just another way of saying x is rational, and y is an element of Q, then we know how to write a sum. We've done that tonight already with the sum of 3 odds. This is even easier than x plus y is an element of Q. So we've got our eyes on the hypothesis. Good step 2 is to identify the hypothesis, which of course is what we're going to assume, and identify the conclusion, which of course is what we wish to show. Now that's going to change later when we're doing proof methods that aren't just the direct proof method where we assume P, we wish to show Q, when we're proving an if P, then Q. But right now, we're keeping it simple. It's just direct proof. We can even write it, if you're not comfortable with this, you can go ahead and write it with words. If x is rational and y is rational, then x plus y is rational. That appears in the notes just as a choice of a way to write your if-then. You don't have to use, the element of Q. What should we assume? What's our first sentence of our proof?
X and Y are rational numbers.
You bet. Assume x and y are rational. And certainly you can write the word numbers. What do we wish to show? I hope everybody can write what we wish. Go ahead and write your wish. You can write it 2 different ways. I'll just do the element of Q way. Yikes, my element of got distorted. There we go. All right, so go ahead and take a few minutes and see if you can at least set up your equations using the definition of rational. I'll put the definition up here where you can see it. Here's our definition of rational. So go ahead and write the next couple of sentences in the proof. And I do want to show you a hint about the algebra. Don't forget to say by definition of rational. Is everybody writing? How you doing? Let's see how the gallery's doing. Hey, Hussein, you're here. I'm glad you're here because you almost missed your extra credit for being here.
I've been here.
Well, when I asked you to chat in or mic in or show your camera, you didn't say anything for like a minute and a half.
I ain't hear you. I'm here though.
That's good because that means you're going to get +2 added to your test 1 grade. Everybody's getting extra credit for being here tonight.
Okay.
Glad to see you. All right, so let's do this. Let's go ahead and so glad you're here. All right, here we go. We have x is equal to a over b, where a and b are in z, and b is not 0. I get it, folks. It gets, kind of tedious, but after a while, it'll just flow. It just starts to flow. And y is equal to c over d, where c and d are in z, and d is not 0. I hope you've got something sort of along the lines of that. You didn't have to use a, b, c, and d. You can use other letters, of course. That'd be fine. Let's expound on our wish. What do we wish to show? That x plus y is equal to, say, m over n, where m and n are in z, and n is not 0. Parts 1, 2, and 3 of the definition of rational. Now, I do want to just go over a little bit of the algebra. When we add two fractions, what does that look like? X plus y. Well, when we do our substitution, we've got a over b plus c over d. Okay. I like to line up my equal signs. It just makes it easier. If you're used to working like way, way, way across, the whole line and then coming back, no. Just go ahead and line up your equal signs. It makes it much, much more legible. Makes it much easier to read. Okay, so when we are trying to add two fractions, what do we have to do? Here, I'm going to do a little scrap work here. Let me just show you a little scrap work. Like if we're adding like 2/3 plus 4/5, what do we have to do? Anybody?
You have to multiply by like the common denominator or something.
Yeah, we got to get a common denominator, which would be 3 times 5. And then what we have to do is we have to multiply 2 times 5. So it'll be 2 times 5 plus 3 times 4 for the numerator. Does that look familiar? 2 times 5 plus 3 times 4 over that common denominator, 3 times 5. Now, how many people think that this numerator was obtained by what you would call cross multiplying? 2 times 5 plus 3 times 4. Okay, don't even answer that. It's not cross multiplying because there's not an equal sign between these two. Let me show you what's really going on. Maybe it's been a long time. Maybe nobody ever really showed you what is going on when we get a common denominator and write 2 times 5 plus 3 times 4. This is what's really going on, folks. You know how when we take 2/3, we can multiply it by 1, and that does not change it at all, right? You can multiply anything by 1. It doesn't change that. So 2/3 is really 2/3 times 1. 4/5 is really 4/5 times 1. So what we're doing here is we're using a form of 1 that suits our purposes. We're really multiplying 2/3 by 5 over 5. Plus we're multiplying 4/5 times 3 over 3. 5 over 5 is 1. So is 3 over 3. We're just using the form of 1 that suits our purposes. What is our purpose? To get a common denominator, which is 3 times 5. So that's what's really going on when we get this, in case you were ever wondering what's really going on. So here, the algebra that we use when we have variables, the common denominator is b times d, and then it's a times d plus b times c. That's the numerator, ad plus bc, and the denominator is bd. So we've already got part 1 of the definition of rational satisfied. We've got x plus y looking like something over something, okay? Great. So the numerator is what we're going to call m, and the denominator is what we're, calling in our wish. Everybody with me? And now there are two more things we have to do, right? We have to verify that this numerator and this denominator are integers. And then we have to verify that this denominator is not 0. But of course, we've got all this great stuff to use. We'll use part 2, that A, B, C, and D are integers, to get that this numerator, which we're going to call m, is an integer, and to get that this denominator, which we're going to call n, is an integer. We'll use closure properties, right? What are the operations that are being used to build m? Take a look. What mathematical operations are being used there?
Multiplication and addition.
That's right. So you'll cite that products and sums of integers are integers to verify that m is an integer. For n, we could just cite multiplication because that's all that's being used to build n. All right, and there are numerous ways to phrase those statements. I suggest that you work on that, try to do it, and then check what you write against the various proofs that we've done tonight, because there's more than one right way to say it. You can say closure of z under multiplication and addition, or you can say sums and products of integers or integers. Take your pick. Anyway, I encourage you to finish this proof by verifying part 2 of the definition of rational, that m and n, this and this, are actually integers. And then I encourage you to finish the proof by verifying that n, which is b times d, is not 0 by using the fact that b is not 0 and d is not 0, right? Because we're trying to prove that this denominator is not 0. We use the fact that these two denominators, b and d, aren't 0, just like I said. So you finish that later, and you'll be able to see the full proof online in the notes. Okay, so now what I'd like to do is shift gears. We've got 15 minutes. We're just about on track, just so that we can have something else to play with, something else to think about. Moving on to section 4.4, which is the idea of divides. Okay, so here's the definition of divides. Given integers a and b with a not equal to 0, we say a divides b. That's what we're defining. A divides b. Denoted by, and it's a weird notation and it confuses students, okay? So listen up. It's A with a perfectly vertical line, B. A vertical line, B. This is a statement that A divides into B. You can insert the word into there in your mind if you need to. If B is equal to A times K for some integer K. That's the definition that A divides B. Okay, so there are different ways to say A divides B. Let's talk about some of these different ways so that you can really get your head around this so that you don't confuse it for the number A divided by B. That is the most common error students make, people, is that they see this and then they start writing this vertical line kind of as a slanty line, and then suddenly it's A divided by B, which isn't even a statement. A divided by B is a number. This, my friends, is a statement. There are lots of ways to say this statement. Of course, A divides B is one way to say A divides B, but there are other ways. B is divisible by A. A is a factor of B. These all mean the same thing. These are all statements. This is a statement, not a number. B is a multiple of A. You've heard these phrases. A is a divisor of B. Let's look at a couple of simple examples just to make sure that you got your head around this correctly. Example 6. Folks, 3 divides 12 because, all right, definition. 3 is the A, 12 is the B. 3 divides 12 because B, which is 12, equals A, which is the 3, times some integer K. What's the K that's going to work out to prove that 3 divides B? What's the K we need, folks?
4.
Yeah, 4. Okay, so that's a silly one. Yay, Ronnie, thank you. Let's do one that's not quite as trivial. Example 7, x divides the quantity x squared minus 3x when, we got to say a few things, x is not equal to 0 because we don't want to be divided by 0, and we need to know that x is an integer because, all right, so now our A is x and our B is x squared minus 3x. So because x squared minus 3x is equal to x times the quantity x minus 3. See, the x minus 3 is our integer k. Right? X is an integer, 3 is an integer. The difference of two integers is an integer because z is closed under subtraction. Okay? Now here's a non-trivial example. Here's a real something to prove. For all integers, A, B, and C, if A divides B and A divides C, then A divides B plus C. Okay? We're going to prove the statement in example 8. It's already written as an if-then. But you might be wondering about something. I'll let you write it down and then let's think about, is there anything about this that's kind of giving you pause or making you kind of wonder? I'm going to put the definition of divides up here where we can see it. Anybody bothered by this statement? A little bit? If not, that's fine. There's nothing to worry about, but I'm just wondering if you're worried about A being 0. This is the deal, folks. We don't even have to say that A is not 0. I'll tell you why. If A was 0, then A divides B would be false because 0 can't divide into anything. And A divides C would be false. The point is, this would be a false hypothesis if A was 0. And we know the if-then would be true by false hypothesis. So we don't even have to say that A isn't 0. We assume that A divides B and A divides C is true. In other words, we're going to assume that that makes sense. because that's the only time that we actually have to do any work, is if the hypothesis is actually true. All right, so if you weren't worried about that, don't worry about not worrying. Here we go. Let's prove this thing. We're going to assume A, B, and C are integers. And we're going to go ahead and assume that A divides B and A divides C. Okay? Just like usual, we're going to assume the hypothesis and we wish to show the conclusion. So we wish to show that A divides B plus C. Make sure that you draw this divide symbol nice and vertical so that it really means what you want it to mean. Okay, we've got just enough time to finish this proof. Let's keep the definition of divides right in front of us. By the definition of divides, all right, we've got that A divides B. So we have that B is equal to A times K for some integer K. And we also have that A divides C. So C is equal to A times, and again, we don't know that B and C are the same numbers, so let's say J for some integer J. Now let's expound on our wish. Listen, this was the origin of expounding on the wish way back when I was looking at teaching this particular proof, and I realized students needed a little bit more. Because if you just read this wish naively, okay, we wish to show A divides B plus C, it looks like you need to start with A. It looks like you need to say something about A. But that's not what this definition really is. If we look at what it means for A to divide B plus C, it means we wish to show B plus C is equal to A times M, where M is an integer. You see? And by looking at that definition of divides, because this is a tricky little definition, that A divides B plus C, by kind of unpacking that definition, we realize, oh, it's B plus C that we actually need to look at, not A. See, because this looks like we want to look at A, but this shows us, ooh, we really need to look at B plus C. Well, sure we do, because we know B is equal to A times K, plus C, which is equal to A times J. And now we can factor out the A, and this expression K plus J, that's going to be our M. And now we just talk about M being an integer. Since K is in Z and J is in Z, M equals K plus J is in Z because sums of integers are integers. And I think I actually did not write that sentence in the notes that are online. So add that to that. So now we've done it. Thus, B plus C equals A times M, where M is an integer. So A divides B plus C by definition of divides. And we're done. So it's a new definition to play with. It's a little bit of a tricky one because of the notation. Homework 4.3 on rational numbers is due on Thursday as usual. Homework 4.4 on the definition of divides isn't due until Sunday. You know, we do Thursdays and Sundays for WebAssign, but we're going to be talking about the definition of divides more on Wednesday night. So you're gonna get some more practice with this, but I did want to go ahead and kick off the discussion about the definition of divides so that you could start mulling that over. Okay. Any questions? Any answers? Meaning of life? Anybody got that one for me yet? All right. So I got a few minutes now before it's time to, I did want to go ahead and offer an office hour, right? Because you know, you might need one since that special homework on even and odd proofs and disproofs is due on Wednesday. So I'm going to take a few minutes for a break here. I'm going to stop recording. I'll be back